Alright, today we're actually going to be looking at balancing redox reactions in basic conditions. Now, in the last video I actually made, I actually talked about balancing redox reactions in the acidic conditions. So if you don't really know how to balance redox reactions in any conditions, you can actually go back to that video and actually look at how to balance redox reactions in the acidic conditions. Because in this video, we're actually just going to be focusing on balancing redox reactions under the basic conditions. So now, when balancing redox reactions under the basic conditions, we most times add water to the side that has more oxygen, to the side that has more oxygen atoms, and hydroxide ion to the side with less oxygen atoms. Now, the reason, let me just leave that reason part. Now, if you can remember from the last video that we actually talked about, that was acidic balancing redox reactions in the acidic conditions, like under acidic conditions, we actually talked about adding hydrogen ions to the side, to the left hand side of the reaction, and water to the right hand side. But the conditions are actually the same, like different. We add water to the side that has more oxygen atoms, and we add hydroxide ion to the side with less oxygen atoms. Sure. When we actually start doing a reaction, actually see how we actually do this, and I'm sure you understand it by then. Now let's look at an example, just like I taught you, just like how we did for the balancing of redox reactions under the acidic conditions. We use an example to actually explain the procedures happening. So now in this example, that's example here, we're asked to balance this reaction under the basic condition. Now this reaction is the reaction between sulfite ion with nickel 3 hydroxide to actually give nickel solid and the sulfate ion. So we're actually asked to balance this under the basic conditions. Now if you can remember from the last video, the first step that we actually need to do is to identify our oxidizing and reducing agent in each case, and this is what should be produced by when we break the full equation into the oxidation half and the reduction half equations. That's the two half equations. Now the oxidizing agent or the reducing agent, let's start with that. The reducing agent in this case is sulfur, because sulfur got oxidized from +4 to +6. Now with the sulfite ion, sulfur has an oxidation number of +4, and the sulfate ion, sulfur has an oxidation number of +6. So oxidation can be defined as the increase in oxidation number. So sulfates like the sulfite got oxidized to +6, and hence is the reducing agent. So this is actually the oxidation half equation. This equation here, actually let me just remove all the ink so we can actually say it. This equation actually oxidation half equation. So now in the oxidation half equation, sulfur got oxidized from sulfite, that's from +4 to actually +6. Now let's go forward. Now the second ions that we're actually dealing with, or the second atom we're actually dealing with, that's the nickel atom. So nickel is what we're actually focusing on. Now in nickel 3 hydroxide ion, nickel 3 hydroxide ion is actually the oxidizing agent, because nickel got oxidized from +2. Now in nickel 3 hydroxide ion, nickel has an oxidation number of +2, and in nickel atom, during oxidation and reduction, now the oxidation number of a free element is actually 0. So in nickel atom, nickel has an oxidation number of 0. So from +2 to 0 is actually a decrease in oxidation number, and that is reduction. Hence, nickel hydroxide ion is actually the reducing agent. It's actually the oxidizing agent because it got reduced in that case. So now we've identified our oxidizing and reducing agents. Now we actually have to go for it. Now the next step is that we balance the atom by adding OH and water molecules respectively. The reason why we aren't really balancing the nickel, normally before that step, we normally balance the charge, or what should I say, the atoms the atoms were actually stored in, if you see from the oxidation half equation, the atoms that we're actually dealing with, or the atom in particular, that's the atom in subject, is the sulfur atom. Now there's one S here and there's one S here, so we don't really need to balance anything. Now imagine a scene or in a case where this is S2O2. I was just thinking of thiosulfate, but that's not thiosulfate. This is SO2 ion. Now, if this is SO2 ion, how do we balance this? We first add 2 here. So that's the first thing we normally do whenever we're balancing. We balance stoichiometric coefficients of the atom. And since you can also see in nickel, it's also balanced 1-1. Now imagine if there was something like this, Ni2, like Ni subscript 2. So imagine if there was something like that. We end up adding 2 here, but there's nothing like that. And if you can look, the nickel atom, or the nickel atom present in nickel 3 hydroxide ion and nickel solid, is actually balanced as 1-1. So we don't really need to balance the elements in that case. So now the next thing that we actually have to do is to balance the oxygen atoms or any other residual atom, that the atom that we're not really focusing on, and that is oxygen in this case. Now, if you can remember from what I said earlier, when we're balancing redox reactions under the basic conditions, we add hydroxide ion to the side with less oxygen atoms, and we add water to the side with more oxygen atoms. So that's what we're actually going to do. Now, between the sulfite ion and sulfate ion, the sulfate ion has more oxygen atoms, so we add water molecule to the side to the sulfate ion, and we add hydroxide ion to the sulfite ion. So now we just add one water molecule to the sulfate ion to actually see how balanced our equation is. Now, when we add one water molecule, we end up with five oxygens present on the left hand side. So 5 oxygens and 2 hydrogens present on the right hand side, and we have 3 present on the left and 1 hydroxide. So what we'll actually do is that we add 2 hydroxide to actually make the total number of oxygen present on the left hand side to be 5, and hydrogens also to be 5, and hydrogen also to be 2. That's the reason why we add OH to the side with less oxygen atom, because OH can actually counteract any effects done by water molecule on the right hand side. So that's just the basic reason why we do this. Now, this is just like, it's just an aid, or what should I say, just to help you like understand what's actually happening. None of these are really kind of like a rule, but they're just like device rule brought up by people. It's not really a must. In a must, you just have to decode it by yourself, by your head, but this will actually help you in your decoding. So that's why I'm just giving you all of them. So now, the reduction half equation, we don't really need to add water and hydroxide ion now, because we're only dealing with OH ion. We're only dealing with this OH in particular, so there's no major need of adding water to the side with more. Or if you want to do that, you can actually do that. You just end up expanding your equation and canceling a lot of things later on. But simple way, just add 3 hydroxide ions to actually counteract the effect of these 3 hydroxide ions present in the nickel 3 hydroxide ion. So we just add 3 hydroxide ions to actually counteract that effect, because this is a very simple thing. Remember, in chemistry, we're always looking for like simplest equation for every single reaction. So this is like a very simple equation. Just add 3 hydroxide ion to the right hand side to actually counteract that hydroxide ion. And I find that you balanced the oxygen atoms, or the oxygen atoms present and hydrogen also present. So now next thing that we actually have to do is to balance the charges. We balance the charges by adding electrons. Now you can actually calculate like the resultant charge present on the left hand side. We have -2 for the sulfite ion, and we also have -2 from the hydroxide ion. So that's a total of -4. But on the right hand side, we only have -2 because water is a stable compound. It has an oxidation number of 0. So I mean a charge of 0. So at the end of the day, the resultant here is -2 and here is -4. So what do we have to do? If you can remember from what I said in our last video, we add like oxidation in the oxidation half equation, we add electrons to actually to the right hand side, while in the reduction half electrons, so let me just write while in the reduction half equation, let me call it red, we add electrons to the left hand side. So that's simply what we actually do here, but you can actually just use your head to break this down. I don't really like using a particular rule to actually for someone to actually understand this, because everyone can understand this. This is a very basic thing to understand. So now, to actually counteract for the effect of -4, if we add electrons to the left hand side, we just end up having -4 minus whatever, and that'll end up giving us a higher value. But if we add electrons to the right hand side, that is plus electron, we end up having electron is a negative charge, so we end up having -2 minus. To counteract for -4, we actually have to add 2 electrons. So we end up having -2 minus, so that will end up giving us -4. So we end up adding 2 electrons to the right hand side. That same rule, like the rule I gave you earlier on oxidation, add electrons to the right hand side. It works, and this also works. These two things just work hand in hand to actually show you where you can really add your electron. And we end up with a final equation of this. Now this is our final equation. As you can see, if you want to actually confirm that charge is actually balanced, we end up with -4 here and -4 here. You can actually do the maths and confirm. This is for -2, -2. This is also -2, -2, -2, -2, -4 left hand side, -2, -2, -4 right hand side. So we've actually balanced the charges for the oxidation half equation. So let's try and balance the charges for the reduction half equation. Now for the reduction half equation, we are asked to like balance charge for the reduction half equation. Now, in the reduction half equation, what actually happens is, I'm coming. Just give me a minute. I want to confirm something. Okay. Now for the reduction half equation, what actually happens is that you can see that this has a resulting charge of -1, and on the right hand side, it has a resulting charge of -3. So what's actually happening here is there's a deficiency in charge on the left hand side. So what we do is our same procedure we did for the last one. We actually have to add how many electrons to counteract -3? 2 electrons. -1 -2 will end up giving us -3 and -3 on the right hand side. So this is the reduction half equation. So as you can see, charge actually changed from -1 to -3. So now then, we then have for oxidation half equation, this as our oxidation half equation. This is just what we balanced the last time, and this is for our reduction half equation. Now the next step that we actually need to consider is actually the cross multiplication of electrons, like cross multiplication of electrons. But in this case, for like this example, we have 2 electrons on the left hand side and 2 electrons on the right hand side. We don't really need to cross multiply, because if we cross multiply, we'll still end up dividing by 2. So what's the point of actually cross multiplying? We just leave it like that because the electrons are actually balanced. But if the electrons aren't really balanced, we actually have to cross multiply by the stoichiometric coefficient in front of the electrons, because the first thing we actually want to do is to cancel out the electrons, and we cannot cancel out electrons when the charges of the electrons aren't balanced. That's what I'm talking about. We cannot imagine if there were 5 electrons here. Cannot cancel 5 and -2. Now 5 and 2. 5 and 2 will give us a resultant electron charge of 3, like 3 minus 3, because electrons are always in negative charge, will give us a resultant electron charge of -3. And that is not what we are trying to achieve here. We're trying to achieve 0, 0, removing the entire electron. So we normally cross multiply. That's if there's a case like this, we cross multiply. That we should multiply this by 5 and multiply this by 2. That's what we do. At the end of the day, we end up having 10 electrons here, 10 electrons here. So, but that's not what we're actually going to be doing here, because the electrons are actually balanced. So the next step, we'll just go over to the next step. The next step involves the cancelling of electrons and hydroxide ions. The reason why we're cancelling hydroxide ions is because hydroxide ion is present on both sides, on both opposing sides. So what we just actually do, just to cancel the hydroxide ion, I actually calculate like the resultant hydroxide ion present on both sides. So first we actually cancel the electrons. Now we've cancelled the electrons, then we actually cancel the hydroxide ion, because hydroxide ion will actually counteract, and we end up with a resultant hydroxide ion of 0, like OH minus. That's 1 hydroxide ion. That's what we end up with, because the hydroxide ions are present on both sides. I've just explained that. So our last procedure that we actually need to do is to combine both equations. So now these are we're combining both equations. We've combined them and we end up with something like this. So these are the products formed from our total equation. You want to calculate the resultant charge. From the sulfite ion, we have a resultant charge of -2, and from the nickel -1, from the sulfate -2, and from the hydroxide -1, from the nickel solid and water 0, 0. We end up with a total charge of -3 and -3 on the left and the right hand side. So this is a balanced equation under the basic conditions. So I'm actually going to be taking 2 examples now, so you can actually just see what we're actually doing, or how we actually balance equations under basic conditions. Maybe I'll just take an example, then you actually do the last example yourself and actually see how, if you can actually balance it under basic conditions. So now let's take this example. Now in this example, we're asked to actually balance the equation of chromate ion, that's chromate ion, with magnesium solid to actually give magnesium hydroxide and chromium 3 hydroxide. So this is actually the equation that we actually have to balance now. So now, first of all, identify your oxidizing and reducing agent. The oxidation number of magnesium here is 0, and in magnesium hydroxide is +2. So what happened? The oxidation number of magnesium actually increased from 0 to +2. So hence, magnesium, like the reaction, magnesium is actually the reducing agent, because magnesium oxidation occurs at magnesium. But in chromate ion, so now in chromate ion, the oxidation number of chromium is actually +6. And now from +6, it changed to +3. So what actually happened was a decrease in oxidation number, and that is defined as a reduction. So chromate ion is actually our oxidizing agent. So now let's go over and write, let's start with the reduction half. Our reduction half, I'll be representing it by red. So our reduction half equation should be Mg actually giving us is actually a reverse reaction. So we remove this, a reverse reaction. So Mg reverse reaction to actually give us Mg magnesium hydroxide MgOH2. And our oxidation half, that's oxy, will actually give us CrOH, CrO4 2 minus. That will give us a reversible reaction with chromium hydroxide. That's chromium giving us a reversible reaction with chromium hydroxide. That's OH3. So these are oxidation halves. This is AH, sorry. So these are oxidation half and that's our reduction half equations. Now we've actually broken these equations down into oxidation and reduction half equations. We actually have to take the next step. Now what's the next step? Actually do balance the stoichiometric coefficients in front of the ions in like the ions in focus. Now the ions in focus for the reduction half is actually magnesium ion. So magnesium ion has one here. There's one magnesium ion present on the left hand side and there's also one present to the right hand side. So magnesium ion is kind of like balanced by itself. Also chromium ion is actually balanced by itself. It has one here and it also has one here. So chromium ion is also balanced by itself. So we don't really need to change anything here. So we now have to balance the balance the other charges, like the other ions present. The other ions present in the reduction half is the oxygen atom or oxygen ion, and that's the hydroxide ion. We actually have to balance that, and also have to balance the oxygen ion present on the chromate ion and the hydroxide on the chromium hydroxide. So that's the next step we actually have to do. That's the second step. So let's start balancing the charges now. Let's start with the reduction half equation. That is red. We have magnesium. Sorry, I need to start again. The reduction half equation, red. That's magnesium Mg. Giving us magnesium hydroxide Mg OH2. Now we don't really need to balance. We don't really need to balance by adding water and hydroxide ion to the side with more and less oxygen. Now, how we just balance this is just by adding two hydroxide ions, because it's quite simple to actually do that than going through a longer process of adding water, and that might lead you to complicate, or should I say contradict yourself, and at the end of the day you end up making a very silly mistake that could have avoided easily just by doing something as simple as this. Now, as you can see, just add only hydroxide to the side with that is hydroxide ion deficient, that is the side OH deficient, that's the left hand side in this case. Now for the other reaction, that's for the oxidation half equation. Now the oxidation half equation involves, let me just go back and check it again. That is CrOH, that's chromate ion, actually leading to the formation of chromium hydroxide, that's this. Now we have to obey the rule that I actually told you to avoid earlier on. Now we have to actually balance the charges of hydroxide, by adding water to the side with more oxygen and hydroxide to the side with less oxygen. So add water. This is because there's oxygen present. It's not just only one ion present. There's oxygen present in the chromate ion, not just only the hydroxide present in the chromium hydroxide, and we add. So that's why it's quite different from this one, both. So we add this. So this is what we have. But the equation is not yet balanced. So let's balance the charges. So now, in order to balance every single thing, you actually have to find the right number. Let's just try and make the water actually four molecules of water. If it's 4 molecules of water, we'll end up with 8 oxygen present on the left hand side and 8 hydrogens present on the left hand side. Now we have 3 hydrogens already present on the right hand side from the hydroxide, and also 3 oxygen present. So if we just add 5 to this, we end up with a balanced equation where the charges are balanced and every single other thing is balanced. So now, if you can look at it, every other thing is balanced. The hydroxide is balanced, the OH, there are 8, and if you actually do the calculation, find out that it's all balanced. So now the next thing we actually have to do now is to balance the charges. So let's balance the charges. Now let's start with the reduction half equation. The resultant charge of the reduction, let me just give of the reduction half equation on the left hand side. Here it has a resultant charge of -2, and here it has a resultant charge of 0. So what do we do to counteract this effect of the -2? We add 2 electrons here. and we've calculated the effect of the -2. So now let's look at the oxidation half equation. Now if you can actually look at the charge, the chromate ion has a charge of -2, water has a charge of 0. So the left hand side has the resultant charge of -2, and the right hand side have a resultant charge of 0 here and -5. So the charge deficiency of the left hand side is actually -3. So we add 3 electrons to the left hand side. So let me just remove some of this and just continue like what I'm saying. We add 3 electrons to this side. So that's meant to be in white, sorry. 3 electrons to the left hand side. So at the end of the day, the resultant charge on the left hand side will be -2 minus 3 electrons, and that'll give us -5, and we've ended up balancing the charges. So now the next thing that we actually need to balance now is what the electrons, like the electrons, not okay, we balance the electron. What we're trying to say is that the electrons on the reduction half equation and that on the oxidation half equation aren't the same. So what must we do? If you can remember from the procedure I actually gave you, we multiplied this by the number of electrons on the reduction half, and that is 3. And we multiplied this by the number of electrons on the multiplied it by the number of electrons on the oxidation half, that's 3, and multiplied this by the number of electrons on the reduction half, so that is, we are multiplying this by 2. And at the end of the day, we end up with an equation for the reduction half equation. So these are the equation for the reduction half equation. That is every single thing multiplied by 3, and that would be 3 mg plus, let me just look at it again, 6 hydroxide plus, plus 6 OH minus, that will end up giving us a reversible reaction of, that's 3 mg in brackets OH in bracket 3 plus 6 electrons, 6A minus. And now for oxidation half, also be looking, I'm sorry, that is gonna give us 2Cr2. So that's gonna give us 2CrO4, that's 2 chromate ion, plus that's gonna give us 8 hydrogen, 8H2O. Then the reversible sign also. Oh, we forget our electrons, which are really, really important in this case. Never try or never attempt to forget your electrons. They're really, really important. No, so that's gonna give us plus 6E also. And the reversible sign. Now that'll give us 2 chromium hydroxide, 2Cu, that's this, plus 5, that's 5 multiplied by 2, that's 10 hydroxide ions, plus 10 hydroxide ions, so 10, so I need to start with the hydroxide ions again. Let's take this off. Plus 10 OH minus. So this is what we have. So now the next step that we actually have to do is cancel. Let's cancel out our electrons and our resultant hydroxide ions. If we cancel out these electrons, we end up with 0 electrons. Now, the hydroxide ions are present on 2 opposite sides for our reduction or oxidation side. We can actually combine the equations and start doing the cancelling, or we can actually just cancel them like that, because we'll still combine the equations later on. So if we cancel this, we have 0 here, and we cancel this hydroxide, we have a resultant of plus 4 OH minus. So now, there's no other thing to cancel, so what we just do, we combine the oxidation and the reduction half equation. So let's combine that. That is 3 mg plus, that's 2 chromate ion, 2CrO4, 2 minus 2 chromate ion, plus also now on this side we only have 8 plus 8H2O. And that will give us our reversible sign of 2Cr2. Let's start with the magnesium. So let me just take this down like this. So The magnesium hydroxide, let's start with that. That's 3 magnesium hydroxide, 3 Mg OH2 plus that's 2 chromium hydroxide and plus 4 OH plus 2 OH3 plus also 4 OH minus. So if you want to calculate the charges on the left hand side, let's actually do that. The resultant charges on the left hand side, this is minus 2 minus 3 on the left hand side, and on the right hand side also. Are we missing something? Sorry, let me just confirm. Oh, it's not minus 2, my bad. This is minus 4 because 2 times minus 2, that's minus 4. And on the right hand side also from the hydroxide, that's also minus 4. So the charges actually balance and can actually cancel out each other. So we can see that the charges are balanced. We want to check if the atoms are balanced. We have 3 Mg and every other atom. If you look at every single thing, you find that the atoms are also balanced. So that's just it. So I would like you to attempt this one yourself. Try and attempt this example I actually gave you here and just check if you get the answer. I'm not going to give the answer, but just try and attempt it. Just like with the rules that you actually see me use, just try and attempt it. I'm sure you understand it. So thank you for watching. That's what we'll actually be stopping for today. And that's all about balancing redox reactions under the basic medium. So thank you for watching. Have a lovely day.